Welcome back to Mathematics Lifeline. This is episode 4 of our integration practice series. So I'm going to give you two integrals that are on the board right here. I'd like you to go ahead and work on them and then come back to me for the solutions. So you see the integrals right here, they're both indefinite, so we don't need any numerical values, and don't forget the plus c. So yeah, you can go ahead and start working on those right now, pause the video, and I'm going to start the solutions right when you come back. Alright, so here's the first integral. Hopefully you made good progress on this, maybe even the answer. We're going to go ahead and work on the solution right now. So we have the integral of 1 over x squared plus 2x plus 5. So we have a rational function here that we'd like to integrate, and there's a few general strategies that we want to use. So we usually want to look for u sub first, then we'll look for partial fractions and trig subs. The problem with this integral is that none of those strategies are really going to help us right now. The reason is because, well, u sub doesn't help because if we took u to be the denominator, well, there's nothing for the du to cancel with. Partial fractions doesn't work because this is not going to factor nicely. It's an irreducible quadratic. And then trig sub isn't going to help us. There's really no form for a trig sub here. But what we are going to do is we're going to use kind of a rare strategy for integration, but it's a great strategy. We can actually complete the square. So if you don't remember how to complete the square, well, I'm going to show you how to do it for this example. So if we have x squared plus 2x plus 5, we want to get this into what's called the vertex form of the parabola, which is going to be, it's going to look like this, x minus h squared plus k, where h and k are just numbers in this case. So we want to get this to look like this. Now, what we're going to do is we're going to write it like this. We're going to write x squared plus 2x. We're going to leave a little bit of room here, and we're also going to put parentheses around it. And then we're going to have the plus 5. Now, the process for completing the square is what we're going to do is divide this middle coefficient, or the b coefficient, essentially. We're going to divide that by 2, so we're going to get 1. And then we square that number. So we square 1, and what we're going to do is we're going to add what we get. So we're going to add 1 to what we just wrote down. Now, of course, because we added 1 to what's inside the parentheses, we also need to take 1 away to make the equation, or to make this still equal. So we need to subtract 1 out here. Now, the reason this is helpful is because now what's in here can actually factor into x plus 1 squared. And this out here just becomes a plus 4. So we've got this into this vertex form, and that's really nice. So what we want to do now is we're going to rewrite the integral and try to use a formula to integrate this. So now we say that this is the same thing as the integral of 1 over x plus 1 squared plus 4 dx. Now, it may not be immediately clear why this is helpful, but if we remember the derivative of arctan, we're actually able to work with this very nicely. So this formula that I'm going to show you is actually based on the derivative of arctan. This is like a chain rule here. So what we're going to do is we're going to just write down this formula. The integral of 1 over x squared plus a squared dx, where a is just a constant, is always equal to 1 over a arctan of x over a plus c. Now, arctan is also the same as inverse tangent, if that's the form you're more used to, but I will write arctan just to avoid confusion. So this formula is going to help us out here. Although we don't have x squared, we have x plus 1 squared, so it's still a function in terms of x. And then we have this plus 4, which this is really plus 2 squared. So in this case, our a is going to be equal to 2, right? So a is equal to 2, and then our x is really x plus 1. So we're going to use that to go ahead, use this formula to go ahead and integrate this. So what we're going to have is 1 over a. Well, in our case, a is going to be 2, because 2 squared is 4. So it's 1 over 2, and then we'll have arctan of, well, in this one it was x over a, but remember our case we have x plus 1 over a, and a in our case is 2. And then of course we'll add that plus c constant, and this is it. So just using that formula, we were able to get a nice answer with arctan. So again, this comes from the derivative of arctangent using the chain rule to get this. But if you can kind of just remember this formula, we're able to get the answer really quickly without much thought either. So yeah, you'll see if you've done the second question already. I don't know if you have, but if you have done it, you'll notice that we're actually going to use that same formula in the second question. Um, so I wanted to cover it here just in case you hadn't seen it before. But yeah, that's it for the first question. Hopefully you did well on that, and we'll go ahead and start the second question right now. All right, so here's the second integral. Hopefully, again, you were able to make good progress on this, and we're going to go ahead and work on the solution. So here we have another rational function. And again, we want to look at u sub, we want to look at partial fractions, and trig sub. Well, if we look at u sub, we would want to choose the denominator to be u because it has a higher degree. But you see that if we do that, it doesn't really help us out with the numerator. So what we're actually going to be able to use here is nice. We're going to be able to use partial fractions. And the reason is because we can factor an x out of the denominator. So we can say that the denominator is really equal to, I'm going to rewrite the entire integral. So we have 2x squared plus 7x plus 4 up here, and the denominator is the same thing as x times x squared plus 2x plus 2 dx. Now that's kind of all the factoring we can do because again, this one is going to be hard to reduce. It's actually going to be irreducible, and that tells us how we need to work with partial fractions here. So remember, we're going to say that 2x squared plus 7x plus 4 over x times x squared plus 2x plus 2 is equal to, well, we're going to use the two factors here. So it's a over x plus, well, we know the denominator is going to be x squared plus 2x plus 2, but because this is an irreducible quadratic, remember in the numerator we need a linear factor. So we need a bx plus c. And now we're going to use that to solve for a, b, and c. So we're going to multiply everything by this denominator. So what happens is we're going to get 2x squared plus 7x plus 4 is equal to a times x squared plus 2x plus 2 plus bx plus c times x. And now we're going to go ahead and expand everything out. So we're going to get ax squared plus 2ax plus 2a plus bx squared plus cx. And now we're going to group everything by the x squared terms, the x terms, and the constant terms. So this is, of course, equal to x squared times a plus b plus x times 2a plus c plus 2a. So I kind of went quick there, but all we did was rewrite this so that we can solve for a, b, and c by matching them, with these coefficients. So if we know that a plus b times x squared, well, that should equal 2x squared. So what that tells us is that a plus b should equal 2. Same thing here, we want 2a plus c to match this coefficient. So we want that to be a 7. And 2a is the only constant term, and we need that to equal 4. So we want 2a to equal 4. Now this is actually going to be a really easy system here because 2a equals 4 will actually tell us that a should be equal to 2, right? We're just dividing 2 over. So if a is supposed to be equal to 2, then we have 2 plus b equals 2. And that actually tells us that b is equal to 0 because 2 plus 0 is equal to 2. And the same thing here. If we have 2a plus c equals 7, well, that's 4 plus c equals 7, which means c should be equal to 3. So now we've solved for a, b, and c. Now we're going to rewrite this integral again in terms of this partial fraction decomposition. So now this is the same as the integral. Well, we have a over x. That's going to be 2 over x. Plus, then we have bx plus c, but b was 0, right? So that's gone. And all we have is just c over x squared plus 2x plus 2. So c was 3. So we have 3 over x squared plus 2x plus 2. And of course, we need the dx. So now we're going to go ahead and split the integrals up to make it a little easier to work with. So we have the integral of 2 over x dx plus, I'm going to pull the 3 out. So 3 times the integral of 1 over x squared plus 2x plus 2 dx. Now, of course, the integral of 2 over x is not bad. That's just a natural log immediately. This one is going to be the same idea that we used on the last question, which is why I did that one first. So we're going to want to complete the square here. So if we take x squared plus 2x, and then we'll leave some space, plus 2, we want to complete the square there. So we need to divide the 2 by 2, so we get 1, and then square the 1. So we're adding a 1 again. And then because we added 1, we want to subtract 1 over here. So then we can really rewrite this as x plus 1 squared plus 1. So what we have is the integral of 2 over x dx plus the integral, 3 times the integral, of 1 over x plus 1 squared plus 1 dx. Okay, now we want to remember our formula. So we had the integral of 1 over x squared plus a squared is always equal to, or dx, is always equal to 1 over a arctan of x over a plus c. That's going to help us out for that second integral. So that's why we wrote it back in that form. But we'll focus on the first one. So the integral of 2 over x, well, we can pull the 2 out, and then we just have the integral of 1 over x, which of course is the natural log. So we have 2 times the natural log of the absolute value of x plus 3 times that integral. Well, in this case, our x is going to be in the form of x plus 1, and our a is going to be equal to 1, right? Because 1 squared is equal to 1. So we're going to have 3 times this formula. Well, 1 over 1 just becomes 1. So that means we can just keep 3 times 1, so we'll keep the 3 out here. And then we'll have the arctan of x over a. Well, our x is going to be in the form of x plus 1, and when we divide that by 1, of course, it stays the same. So it's arctan of x plus 1, and then we'll add the plus c at the end. And this is our final answer. So that is our antiderivative. So, I mean, this is kind of a long question, I agree. And you know, you got to do partial fractions, and then you got to break into, you know, completing the square using this form right here. It's not an easy question, but I think that as long as you know this step, it's pretty systematic. We've worked with partial fractions before. You use it a lot in integration, frankly. So, yeah, hopefully you were able to get pretty far with this, even if you worked on it after the first question. Hopefully that one was able to help you out a little bit. But yeah, that's it for the fourth episode of the integration practice. Hopefully you all are enjoying this series. I know I'm enjoying making it. If you have any questions about this, or if you have any recommendations for future videos, of course, feel free to let me know. But if not, then I will see you next time. Thanks for watching.